Okay, great. So first of all, thank you for the organizers for this great conference. Today I want to talk about the topological Floquet systems. These are some topological phenomena realized in out of equilibrium setting. So I think there are already few introductions, and these have been mentioned, but just to make sure, I will be interested in time-dependent Hamiltonian. So Hamiltonian changes periodically in time, and there's some specific periodicity, which is capital T. I call it Floquet period. And then the unitary operator is given by time-ordered product of the time-dependent Hamiltonian. This has been also mentioned, but just like we have a topological distinction in static systems, such as the ground states are distinct in topological sense, we have a topological distinction between, we may have topological distinctions among unitaries. In particular, we can talk about unitaries which are gapped in some sense. And this has been already mentioned, but it can be unitaries which are many-body localized, many-body localizing. So we can talk about topological distinction among such a quote-unquote gapped unitaries. There have been numerous works on this topic, and I could not mention all of these works, which I got a lot of inspiration, but I will be able to mention perhaps a few subset of such a topological Floquet models. Okay, so let me just mention one particular example, which is like, I don't know how to phrase this, but like an integer quantum Hall effect for topological Floquet systems. And I think integer quantum Hall effect can be a hydrogen atom of topological systems. So this is like a hydrogen atom of topological Floquet systems. So what is this model? So this has been discussed by these people. So it's basically a 4-step drive. So I have a unitary which consists of 4 parts: U1, U2, U3, U4. And then each corresponds to some sort of hopping, which is defined by this Hamiltonian H1, H2, H3, H3 to H4. I think it's better to explain by using pictures. What it does is the following. So in the first unitary U1, it acts on this red-colored bond, and it exchanges particles for these bonds. Okay, connecting bonds connected by this site. There's a particle basically hop, and then they exchange their positions. That's step 1. And then I change my Hamiltonian, or I change my unitary. So then now it acts on the subset of vertical bonds, these blue bonds. So then again, we exchange particles for these bonds, and I continue doing this. So in the third step, I choose again the horizontal bond, subset of horizontal bond, which are complementary to the bonds I use in the step 1, and then I exchange these particles, and they do this. Okay, so then I basically go back to the original one. Here I have also a step 5, which may be used to study effect of disorder. But for the moment, it is just a 4-step drive: 1, 2, 3, 4. Okay, so focusing on the one particular site, and I put a particular particle, let's say here. Then in this evolution, the particle perform a clockwise chiral motion. And this model turns out to be a realization of a topological Floquet drive in the following sense. So you can draw energy diagram. In this case, it's not the energy diagram, but it's eigenvalues of unitaries. So you can talk about quasi energies. In this model, energy band, quasi-energy band, is completely flat. So in some sense, a gap to bandwidth ratio is infinity. So it's a very gapped system in this sense. So that's what this quasi-energy band looks like. But if you now make a system cut open, so you make some boundaries to the system, then you start to see the edge mode propagating along the edges. So in terms of energy diagram, you see this chiral edge mode here, red and green. So red one basically represent the particle moving on the boundary this way, and the other one, which, sorry, not this way, but along this edge, and the blue edge mode represent another chiral motion associated to this boundary. So just like integer quantum Hall effect, if you make a boundary to the system, you see the chiral edge mode, which is the signature of topological Floquet drive. There's also some sort of topological invariant, which is just like a Chan number, which you can define for the kind of band structure of the unitaries, which I don't mention much, but there's some quantized quantity which you can use as a diagnosis to tell if you're having or not having a topological Floquet drive. And interestingly, also there's a kind of response, just like a response we have in the integer quantum Hall effect, which is the quantized Hall conductance or some other responses. So similar to that, we have also the quantized response in topological Floquet systems, which I'm going to discuss later. But anyway, this is one of the interesting example of topological Floquet system. So in this talk, I am going to talk about some sort of framework to discuss such systems. I don't think I'm not going to add any new topological Floquet examples, but rather I focus on some sort of effective field theory type framework to discuss such topological phenomena in periodically driven systems. Okay, so what I want to replicate is the success of effective field theory approach for static topological phases. So static topological phases can be basically detected by coupling the system to some sort of gauge field. In particular, symmetric protected ones are pretty much described by their coupling to background gauge field, or time reversal symmetry or some other things. We can put additional data which can couple to topological system. But in the simplest setting, I have a symmetry G, and then I introduce a gauge field for the group G, and then that we can use to detect static topological phases. So then usually we talk about this path integral or imaginary time path integral. I have a microscopic degrees of freedom matter field, let's say, can be fermions, which now couples to the external gauge field, capital A. And then since I'm talking about the gapped phases, I can safely integrate over this matter field, and then I will get some effective action for A. So A is not dynamical, so sometimes I may want to say response effective action. But anyway, this is a kind of a very useful object to talk about topological phases in static setting. In particular, for gapped phases, this effective action is local, which is very important. And then also for topological systems, we have a topological terms in this effective action. The canonical example, once again, is a quantum Hall effect. So here symmetry is U1, and we are living in 2+1 dimensions, and I can write down, we will get a topological term, which is the Chern-Simons term, with quantized integer coefficient. Okay, so this is the kind of story I want to replicate, and this has not been, I think, widely discussed, so that's my motivation. Just a quick remark is that this path integral may be written in this way, in the operator formalism, where I have a time modal product of Hamiltonian, which is initially time independent, but if you introduce background, then it can be dependent on imaginary time through A, and then I can turn on other components of gauge potential too. But then it's roughly looking at trace of exponential of a Hamiltonian. Okay, that's roughly the structure. Okay, so for dynamical setting, natural starting point is the something called Schwinger-Keldysh path integral, or since I'm going to use basically canonical formalism, let's call it the Schwinger-Keldysh trace. So in this Schwinger-Keldysh trace, I have the following ingredients. So I have some initial state, which I start with. Then I evolve in time, but density matrix evolve in time with U and U dagger. That's the von Neumann equation. And then, so what I'm basically having here is the time-dependent density matrix, and I take a trace. Right? It is usually that it is also a convenience to introduce gauge field, two kinds of gauge field, one for each unitary U and U dagger. That's what these two unitaries are. So basically, roughly speaking, for the static case, I have a one unitary, not really unitary, but E2 minus H. But here I have two kinds of unitaries for forward and backward propagation. And usually we draw this type of a kind of contour, Schwinger-Keldysh contour. So I have two kinds of real time propagation. One is forward in time and the other is backward in time, U and U dagger. But if I don't introduce any source, this is just identically 1 because trace of density matrix is always 1. But you can introduce probe A1, A2, and that makes this functional non-zero. And computationally hitting this partition function with respect to these source fields, we bring down operators to define retarded and advanced or mixed all kinds of correlation functions. But anyway, this is something very standard. Okay, so this seems to be the nice object to study in the dynamical setting. So let's try to apply this Schwinger-Keldysh approach to dynamical topological systems. But then I have to specify a few. This is too generic, so I have to specify a few more things. So basically, I want to specify 3 things: time contour, initial states, and the type of backgrounds. Okay, so the time contour, I chose my time contour to be such that I always talk about integer multiple of Floquet period. So I start from somewhere t0, somewhere here, and then t1, and I go back. But this segment or interval, I always choose to be the integer multiple of Floquet period. This is my choice. Another choice is this initial state. So in the kind of more conventional setting, we often start from Gibbs state and ask what happens to the Gibbs state in this time evolution. But in this topological Floquet setting, I guess there's no obvious choice for the initial condition. So I decided to choose this initial state as the most future-less state, which is this infinite temperature state. It's just identity, which is normalized by this number n, which is just the dimension of the Hilbert space. So this choice allows me to focus on the properties of unitaries themselves rather than the evolution of each individual state, which may have very interesting stories. But for now, I chose this state, and then it's essentially, so this allows me to focus on the properties of unitaries themselves. The third choice is about background, and I think this is partly because of some technical problems maybe, but I'm going to choose my background to be, first of all, static, so they don't depend on time. I allow them to depend on space positions, but time dependence is completely switched off. Okay, this is my choice. This is a choice I can work with. That's a kind of one technical motivation. But the other motivation is that for this kind of background, I can show for many examples that my effective functional here is completely local, which is a nice property I want to have. Okay. So maybe one quick thing to mention is that since I have a closed contour, so I have a 2 gauge field. That one can ask what is the gauge transformations. We can do each individual kind of small gauge transformation for A1 and N2. But the contour is closed, so whenever I make a gauge transformation, the large kind of gauge transformation can wind around this Floquet contour. Or other way to say that is that if I have a lambda 1 for the first gauge field, I have a lambda 2 for the second gauge field, they have to be correlated at this point. Okay. So we have set up this apparatus. So let's apply this method to this chiral Floquet drive. So then I chose once again this state to be very featureless. Here I write this way because I have a charge which is conserved, and then I introduce a chemical potential for the charge, which is alpha. So this is basically most featureless states in the presence of U1 charge conservation. But if you don't like this way of presenting, this alpha can be basically considered as a temporal component of gauge field, the difference of temporal component of gauge field. Anyway, I haven't done anything strange yet. Okay, so this is my choice of initial state. So as it turns out, this model also has an additional symmetry to U1, which is this particle-hole symmetry. So I exchange particle and hole. I do such that I put some signs depending on the sublattices. But this is also the symmetry of the problem. So I will keep track of this symmetry, which turns out to be useful. Okay. So now we are going to discuss the following things. So the properties of basically effective actions, which I wrote as a W, with or without boundaries. And then I will also discuss what kind of responses we can read off from the effective actions. And I think toward the end, there's some more issues, but as far as time allows, I can discuss other issues. So, so for this chiral Floquet drive, for my choice of background, effective functional can be explicitly computed, which is not very difficult. So here, I choose my periodicity of the Schwinger-Keldysh contour to be integer multiple of Floquet period capital T. So this time integral basically doesn't do anything, it's just integer. And this B is some sort of flux. So starting from site R, particle make a counterclockwise, is it counterclockwise? Yes, a counterclockwise motion that picks up a flux. So that's a flux, basically, just flux. And there's the two kinds because there are two gauge fields. So I have a B1 and B2. Alpha is a chemical potential. So this is not very difficult. You can explicitly compute this. Okay. So this way of writing is exact, but to make some intuitive understanding of this term, I focus on the background field, which is very smooth. Okay. So then I can basically expand that exact expression, and then I can read off the W for smooth background, which is basically has this form, where I have an integral of flux over a spatial manifold. Time integral is there, but remember it's just basically a trivial thing. It's some integer. But I have this coefficient theta divided by 2 pi. Okay, so it's depending on the chemical potential alpha, but the part which is most important in this part, which is this small theta is pi for this model. So this is the basically what we think of this as a topological term relevant for this chiral Floquet drive program. And this is completely analogous to the theta term, which exists for the description of static topological insulators, such as SSH model. But in this case, for the case of static case, we have a space-time integral for the gauge field, and they have a theta term, and theta is pi for the static, for example, SSH model. We have a similar term, and I think this is perhaps a useful thing to describe chiral Floquet drive. One subtle thing is that this theta term in the static sense is quantized. And the quantization comes from the combination of the gauge invariance and the particle Hall symmetry of the SSH model. So basically, gauge invariance quantizes this flux, and then theta has to be 2-pi periodic. But particle Hall symmetry selects either theta should be either 0 or pi times some integer. Here, B1 minus B2 is basically neutral under gauge transformation, which I described. But at particular time, let's say if my interval of the time is periodicity times integer, if I switch off A1, U is just identity in this model. So I can basically use the large gauge invariance for each individual gauge field, which quantizes theta term. And then there's also the particle Hall symmetry, which quantizes this theta to be pi in the absence of chemical potential. But the chemical potential dependent term must be odd in alpha. So that's basically a similar story, the same story as the static topological term. So I talked about static gauge configuration, but let's say now I go back to my original exact expression for the response functional, Schrödinger-Keldy's response functional. So let me further discuss the properties of Schrödinger-Keldy's response functional. So first of all, it's consistent with particle Hall symmetry. So if I compare Z and with A1, A2, A3, and Z with flipped A1, A2, A2, and alpha, it's just 1, okay? And that's particle symmetric. And then it's basically 1, this ratio is basically 1, but writing this ratio, we basically recognize integral of the flux appears in the exponential, but basically that's a 2-pi because of flux quantization. So this will be modified later, but for now, you get this ratio, which is just 1. So it's particle symmetric. We can also discuss response to singular or very non-smooth configurations to the background flux. So for example, you can introduce a flux phi on one of the bracket, and you can introduce a minus phi on the other, some other bracket, which is separated by some distance. But then you get this type of response. So Schrödinger-Keldy's action partition function is 0 when phi is presumed introduced. The localized flux is exactly pi, which I think it's kind of expected. But let's now focus on the these smooth configurations once again. I decided to work with the integer multiple of Floquet period, which I didn't do it initially. I thought it's kind of okay to do this response functional calculations for any time. Then I have to use numerics, but then I think kind of response functional for the intermediate term seems to be less ideal to describe topological properties. So here's some calculations. So once again, once I deviate from the integer multiple of Floquet period, I have to learn numerics. But we can still compute the phase of the Schrödinger-Keldy's partition function for any time. And then I monitor the phase of this partition function. So this phase of the partition function approaches to what we expect. So here I time changing from in the last fourth period of the Floquet drive. So then it changes from 0 to something very close to pi, depending on this chemical potential. So that's nice. So I get topological response. But if you look at the magnitude or absolute value of the partition function, away from this integer period, it's very small, and in some time it's basically goes to 0. So phase is presumably undefined there. So to define something like a very topological response, it seems to be ideal to stay at this integer multiple of capital T, or intermediate time, it's more complicated. Okay. So a few more things. So now let's make a boundary to the system. So if I make a boundary to this model, basically a Floquet unitary factorizes into bulk part and the boundary part. And Hilbert space also factorizes into bulk and the boundary part. So the bulk part basically means that these particles sitting on the bulk side of bulk Hilbert space, they perform the same motion, chiral motion as before. Whereas these sides in the boundary Hilbert space, they cannot perform the bulk chiral motion, and they have to propagate along the edge. Okay? But then Schwinger-Keldysh action also factorizes into the bulk and the boundary parts. So I can discuss Schwinger-Keldysh action for bulk and boundary parts separately. Okay. So for the bulk part, as for the smooth configuration, computation is basically just the same. So for example, for the smooth configuration, I get this same form, except now integral is over open spatial manifold. Then let's check the particle hole symmetry, but then it turns out it's broken. So if I compare this ratio, this is not 1 anymore, because what is sitting in exponential is the sum of fluxes of all spatial manifold, but now it's open, so it's not quantized. So particle hole symmetry is broken. Okay, so let's now check the Schwinger-Keldysh effective response. That's too long. That's the effective response function for the boundary. And then I can also consider the particle hole symmetry of the boundary. And then it's also broken. It's now given by the, this ratio is now given by the integral of, it's basically a Wilson loop along the boundary. But that's not quantized. So once again, it's not, particle symmetry is broken. But as expected, if you combine bulk and boundary, this ratio is 1. So once you combine bulk and boundary systems, we restore particle symmetry. So in the static topological systems, this has been known, and this actually goes back to, for example, this paper by Eritza, which discusses the global symmetry in quantum mechanical systems, or 0+1 dimensional quantum field theory. In this setting, they have a this type of conflict between particle hole symmetry, mixed anomaly of particle hole symmetry and U1 symmetry. Here we don't have imaginary time, but nevertheless, the situation seems to be very similar, which is also expected from the fact that the boundary unitary is in some sense anomalous. It's something like a chiral fermions in one-dimensional space, so that is supposed to be anomalous. And it seems like this effective action calculation is consistent with this expectation. Okay, so I think, oh yes, the final important thing is the physical response. So once again, for the static topological phases, we can read off, in some sense, the presence of topological terms are important because that's kind of a diagnosis of characterization of a topologically distinct ground state. But for quantum Hall effect, for example, you can also read off kind of physical, quote unquote, physical responses. And the one response is known, is Streda formula, which you can sort of read off from this Chern-Simons term, which says the, for example, magnetization, variation of the magnetization with respect to the chemical potential has to be quantized. Now we have a similar thing in the topological Floquet drive, which has been discussed in these papers. But we can basically reproduce the result by using effective functional approach. So on the one hand, by taking a derivative with respect to the total flux, we can bring down the theta term from the exponential. So that's how we define this quantity m. That's basically theta term divided by Floquet periodicity, which is the kind of coming from the effective response functional expression. But if you think about this expression microscopically, what it does is to bring down the Hamiltonian from the unitary And then we get the Hamiltonian variation of the Hamiltonian with respect to external flux, which defines magnetization. So this theta term is nothing but basically magnetization averaged over space and over Floquet period. And here it's actually quantized to be half, but that's because we average over all number of particles. But we have a chemical potential to distinguish different particle sectors in these computations. So we can basically get what they got before. Okay, so that's all I wanted to say. Other issues are all optional. So how much?
Of time now.
Okay, so I just present this, and thank you for your attention.
Questions?
Seems that the boundary is coupled from the bulk in the partition function. Is that true?
Sorry, say that again?
The boundary and the bulk are decoupled essentially in the partition function?
Yeah, it's totally decoupled. You can, in this case, unitary decouples. So there's no coupling.
But then the bulk is kind of not needed. You could as well just consider a particle that's moving on a ring with some flux, and you would get the same anomaly. Why do you even need the bulk?
That's a good question. Something happens to the strictly speaking, you cannot define Hamiltonian near the boundary, but that may be the issue. So
it seems that you just get a particle on a ring with,
yeah,
with a half-integer flux.
So in terms of unitaries, there's no problem. It's totally perfect. You can define such system. But you try to write down local Hamiltonian, which reproduce such unitary near the boundary, there may be a problem.
I got it.
So if you want these phases to be stable for interacting systems, you need many-body localization. Does that have any effect on this, or do you just not see that at all?
Yeah, so we don't expect this action to be local for non-localizing system. But as far as localization is there, we expect it's stable under deformation. That's similar. Basically, we can show that if you make such a boundary, such a smooth deformation, as far as you stay in the localized regime, this theta to be the same. We can make such argument.
Other questions? Thanks, Shinsei, and everyone else in this session. Okay, so let's reconvene after lunch. So lunch is, again, just like yesterday, it's on your own, and then come back.